Hi guys, hope all of us are doing great. My name is Ernest and this is Ernest Sciences and Mathematics TV channel. In this particular discussion, I'm going to look at the concept of Biot Savart law, and this is going to assist us in trying to do a further evaluation of the relationship between magnetic field of a current carrying conductor and the amount of magnetic field that is going to contribute at a specific point around that specific conductor. And this is described using the Biot-Savart law, which is basically the relationship trying to describe the contribution of a section of this specific conductor given in terms of dl to this particular point of area around this particular conductor, which is experiencing a magnetic field given in terms of db given as such. Now, the relationship between dl and dp is going to be explained using the Biot-Savart law, and this relationship was discovered by two individuals who are the Jean Baptiste. I hope my pronunciation is correct. These are Jean Baptiste Biot and Felix Savart. And these two individuals describe the relationship which is going to be existing between this element of a current carrying conductor and the contribution of the magnetic field which is going to be having this specific point given in terms of dp. In this case, we're going to do this specific evaluation by trying to develop this kind of relationship which has been described by Jean Baptiste Biot and of course Felix Savart, which is going to assist us in trying to define this basic law. Now, this law is going to be finding various applications as we're going to be doing an integration of various elements which are going to form an entire part of this specific conductor, and therefore we're trying to see what is the effect they are going to have in terms of a magnetic field at that specific point. Now, given this specific contribution which I've given in terms of dB, which is a magnetic field, so this is going to be a contribution at this specific point given as a dP, and then we shall have the length of this particular element given or a segment, a length of this specific segment given in terms of dl, and then we are going to have r being the distance between this particular point b. So this is going to be the distance between b and the of course a current carrying conductor, and then we shall have perhaps this specific p as our point of reference, which is an area, a point around this specific current conductor which is experiencing this particular magnetic field. Now, we're going to see that as we have been discussing, the currents which are going to arise due to the motion of particular charges are going to be the sources of a magnetic field around a current carrying conductor. And when these specific charges are going to be moving, they are going to be producing a magnetic field around this particular conductor. Now, this is going to be the case for this particular section which we have given in terms of P. And of course, due to this specific currents, we're going to be calculating the magnetic fields of these specific segments which are going to be adding up and contributing to the overall magnetic field which is going to be realized due to the small numbers of section at this specific point P. Now, these sections are going to be appearing in terms of vector quantities, which are going to be having magnitude, of course, and direction as I've mentioned from this specific aspect. Then therefore, we are going to consider this small amount of current due to this specific section of DL, which we're going to denote in terms of, so we're going to consider a current element in this specific case given in terms of IDL, which is going to be described as such. And R is going to denote, of course, this specific distance from the current source to the field at this specific point P. And in this case, I've used this specific annotation to represent the vector unit, the unit vector, which is going to be pointing in the direction of this specific field. So in this case, it's going to be a unit vector given as such. So we're going to develop the relationship between this, of course, current element and that specific point, and the magnetic field contribution at that specific point. Now, we're going to have this one in terms of an expression for the magnetic field contribution given in terms of dP, which I've indicated at this specific point. And dP from a current source IDL, which I've given in this specific case, can be given in terms of the product of mu naught all over 4 pi and then this is going to be multiplied, or we are just going to have this one as the product of IDL given at this specific point at times. So we're going to do a cross product with this specific unit vector, and then we shall have using this denominator for the square of the distance between this specific element and the point P. So if we try to look at this specific relationship, it's analogous to Coulomb's law for the electric field due to a charge element, which in some of our discussions we had just given this specific notation. So we're not going to go into details, but this is going to be an analogous law which we're going to be seeing taking effect at this specific point, which is basically Coulomb's law for the electric field due to a charge element. Now in this case, we are going to be adding up these particular contributions along this specific conductor to the full length of this specific wire and or conductor, and therefore that's going to require us to do an integration of this specific form of the equation in order to find the total magnetic field. Now in this case, this is going to be one of the applications of Biot-Savart's law in order to find the total magnetic field at a point, and therefore we are going to do that one using an integration of this specific equation. So we're going to have the dp equivalent to the integral of mu naught all over 4 pi, and then we're going to have I dl times r unit vector over r squared. So in this case, we're going to, from our normal integration, this is going to result in the formation of the total magnetic field, and then we're going to have these constants given as mu naught all over 4 pi, which are taken out. So from the rules of integral, we shall have that one out. And then if we are going to consider the total length of that specific conductor given as L from this specific element of dl, which I've mentioned, and therefore we are going to do the whole integration of this specific length of L given as dl times that specific unit vector all over the square of the distance between them and that point B, which we are going to give us as. So this is going to result into a law which is going to give us the magnetic field at the overall magnetic field at that specific point due to the various elements of contributions. And of course, this is going to be giving us what we refer to as the Biot-Savart law, which I had mentioned. Now, in this particular case, we're going to come across these specific laws and the various applications in a number of our discussions, which is going to assist us, of course, evaluate the total magnetic field at different parts, especially on the point which I've given using our particular illustration in this specific discussion. Now we're going to consider other, of course, shapes or elements like the circular current loops and other, which we are going to perhaps illustrate on how we can find them using various laws of integration, and that's going to form our final bit of this specific discussion and application areas as we're going to see later. So that is it for now, guys. Kindly check our description boxes for various links of other videos, and also engage us in the comment section, subscribe and ring that notification bell to be getting other updates on different topics that we do in mathematics and sciences. So that is it for now, guys. By God bless you. Catch us in our next video.